Welcome to lecture number 15 for ECE 761 Robotics, Impact Forces. Now, where we are at this point, given a robot, it's fairly easy to control it in free space. I just use XY control using Jacobians. I can use PID control using joint angles. With Lagrangians, I can calculate the dynamics. If I have a robot in contact with a surface, it's fairly easy to control as well. I lose a degree of freedom, but then the tip force is just related to the Jacobian transpose. Here's a problem for you. What happens if you go from free space and then come in contact with a surface? That's actually a very hard problem. What we did previously would be I'd have one model in free space, that's a 2-degree freedom robot. As soon as I come in contact with the surface, I suddenly lose degree freedom, come up with a completely new set of dynamics, and control the second system. As soon as I leave the surface, I then drop that model, switch back to a 2-degree freedom model. It's a very complicated system, and if you think about it, it really shouldn't be that complicated. If I take my hand and scratch my head, as soon as I touch my head, the dynamics don't change. Nothing really changes, so I don't really have to completely change the formulation. There's got to be a better way to do it. That's what this lecture is looking at. How do I model a system that goes from free space to contact to surface back to free space? One way to do that is change the problem. That's typical in engineering. If you have a difficult problem to solve, change the problem. Change it in such a way that it's easier to solve, but keeps the flavor of the original problem. For example, suppose I want to come in contact with the floor. Instead of making a perfectly stiff floor, let's make it compliant. Have a spring so that if I push into it, it's going to push back with the force proportional to the distance into the floor. Once I know the force, I can account for that using Jacobians and tell you what the effect of the torque is. So the torque due to the surface will be your torque is Jacobian transpose times the force on the tip. And again, Jacobians come into play. So for example, let's take the previous simulation that we had, our R control, modify it. This is now RRY control, wall control. I'd like to trace out a square in 4 seconds. And here's where we're going to put a wall at 1.3. Currently the wall has no impact on the robot. The force is 0, so I pass right through it. Now if I want to model the wall, what I can do is add a spring. So here the spring constant is 10,000. Friction is minus 140. And here the force was 0 because I made it 0. Take that out. This is similar to the homework problem. I want to be able to model coming in contact with a surface. If I hit the wall at 1.3, boom, I hit it. The wall is applying a force as I try to go into the wall. And then I come off. And notice I slightly went into the wall. That's because the spring constant is not infinity. I'll go slightly into it to apply a force. When I'm done, I'll show you what the tip force was due to the wall. Looks like this. Here's the impact. That's a delta function. When I hit the wall, there's a big bang, and then I move along the wall. So here's a problem for you. Suppose I want to come up to the surface of the wall, to skim along it, and then apply a force of, say, 60 newtons. How do I do that? That's similar to what the homework problem is. One way to do that is change your path planning. Instead of going through the wall, let's just come right up to the surface of the wall and then move up. So here I'll go up to 1.3. That's where the wall is. Then stop. Move along the surface of the wall and then come off. So that's the first part. I want to move along the surface of the wall. Here, ideally, I'll be applying 0 force to the wall, just gently skimming it. And that's what we're seeing here. I'm applying a little bit of force. This is like 0.6 newtons. Suppose I want that to be 50 newtons. Well, one way to do that is find the time that I'm touching the wall. That's between 1 and 2 seconds. Say between 1 and 2 seconds, I want the wall to push back with a force of 50 newtons. This isn't quite right, but we'll get there. So I move up to the wall. This is now at 1 second. The wall pushes back with 50 newtons force. Push the robot way back. Then at 2 seconds, I release and I come back and track. So that's sort of working. The wall's pushing 50 newtons at this time. But really what I want to do is have the robot lean into the wall with 50 newtons of force. So what I'll do instead is between 1 and 2 seconds, when I'm in contact with the wall, I'll lean into the wall with 50 newtons force. Otherwise, don't lean at all. To convert force to torque, that's Jacobian transpose. So here I'm leaning into it with 50 newtons force. That pushes into the wall. The wall pushes back with the spring constant. And what you're left with is I'm tracing out a square. During 1 and 2 seconds, I've got 50 newtons force, roughly, plus a slight impact, and coming off it. There's other ways to do that that are described in the lecture notes, but that's essentially what the problem is on the homework set. How do I come in contact with an object, come up with a simulation so I'm in free space, like right here, come in contact with an object, maintain a force on the object while I'm in contact with it, then go back into free space. And that's one way to do that. Change the system so that the wall is now compliant, has a little bit of give. And then, using Jacobian, calculate how much you want to bias the torques to maintain a given force against the wall. That's lecture number 15, impact forces and maintaining forces while in motion. That kind of wraps up 761 robotics. The next lecture is kind of a recap, but what we have so far is we can do forward kinematics, given a robot, define its reference frames, then calculate the tip position. Inverse kinematics, given the tip position, calculate the joint angles. I can come up with the dynamics using Lagrangian formulation. I can control the robot either in XY coordinates using Jacobians or joint angles using PID controllers. And I can come in contact with a surface and maintain forces against the surface using Jacobian transpose. And that wraps up 761 robotics.